Hi folks, we're going to take a look at the question number 3 from the related rates sheet. Okay, we see now a different example from what we've seen before. So here we have water runs into a conical tank at a rate of 0.9 meters cubed per minute. The tank stands point down and has a height of 3 meters and a base radius of 1.6 meters. How fast is the water level rising when the water is 2 meters deep? Okay, so again, one of these scenarios where a picture really is invaluable. So let me draw my conical tank here. Okay. Now, again, what I want to input into this diagram is things that don't change. So the radius of the tank does not change. It's 1.6 meters. The height of the tank does not change. Okay. That's 3 meters. Okay. And I know that the water is being poured in at 0.9 meters per minute. So here, what is it that's changing? Well, it's changing the volume of water in the tank. So here what they're giving me is they're giving me dV dt is equal to 0.9. Okay? So now let's try to solve the problem. So we want to know how fast the water level itself is rising. Okay, so what we're going to look at now is just the water inside the tank. Okay, and we have information about the volume. So we want to relate the height of the water, or the rate of change of the height, to the rate of change of the volume. Okay, now while we're given a specific height in the question, this is a changing quantity. So when I set up my equation, I want to keep h as my variable. So what's the relationship between v and h? Well, we know that the volume of a cone, because the water will take on the shape of a cone, is just pi r squared h. In other words, the volume of the cylinder with the same radius and height, and divided by 3. Okay, so here we see that we're going to have to consider the radius of this cone of water. Okay, but I definitely need to get rid of one of these variables, because as usual, we want our relationship to be one variable in terms of another. Okay, now given that we're interested only in the rate of change of the height, we should be very motivated to get rid of the radius. Okay, so we have to find a relationship between r and h, so we can write one in terms of the other. Okay, and this is where, again, sometimes you think a little outside of the box or a little outside of the cone, and you have to see if there's a relationship that you can make between r and h. Okay, and if you look closely enough, you start to realize, well, wait a minute. If I extend this to the whole height, okay, and I look at this triangle, okay, relating the radius and height of the water, I can relate it to this larger triangle, the full radius and full height of the cone, and we see that we have two similar triangles. Okay, so I believe this might be the first time that we're using this geometric relationship to help us out. Okay, so we know that the ratio of sides of similar triangles, okay, will be equal. So if I compare, and again, I don't want to do this in the body of my solution, but I'm going to do it on the side. So here I can create a ratio, that the ratio of the radius of the smaller triangle to the radius of the larger triangle, so r over 1.6, has to be equal to the ratio of the height of this triangle with respect to the height of the full cone, is going to be equal to h over 3. And again, since it would be preferable to isolate r in terms of h, so that my equation will just have volumes and heights, that's what I'm going to do. So r is equal to 1.6 divided by 3h. Now I'm not going to bother estimating this because it's not a very nice decimal, so I'm just going to keep it in this form until I need to actually calculate anything. Okay, so here the volume can be written as pi times, well, 1.6 over 3h squared. Replace the r by that expression there, times h divided by 3. Okay, Now, I don't want to worry too much about the constants, so I'll bring all the constants together. So we've got the pi over 3, okay, times, well, the 1.6 over 3 squared. Again, I'm not going to worry about that till the end. Why lose precision by estimating at this point? Okay, and here I'm left with an h squared times h, so h cubed. Okay, so this is my relationship now between the volume of the water and the height of the water. Okay, so I'm going to take the derivative with respect to t of both sides of the equation so that I'll get the rate that I know and I'll get the rate that I'm looking for as part of my expression on the right. So here I won't write it down. We'll just do it here. We'll take the derivative of the left-hand side with respect to t, nice and easy. And if we take the derivative of the right-hand side with respect to t, well, first of all, this whole thing is just a constant. So I'll simplify a little bit because it's pi times, well, 1.6 squared. And here I have 3 squared times 3 is just going to be 27 in the denominator. Now, that's just a constant, so that doesn't affect anything. So now let me take the derivative of h cubed with respect to t. Here we're going to have to use the chain rule. First, the derivative of h cubed with respect to h, so 3h squared, times the derivative of h with respect to t. Okay? Now, it's a good thing they gave us a specific height at which to determine the rate of change, okay, because we see that that is a variable in our equation, and we know how the volume is changing with respect to time, so the only variable we have left is dh dt. Now let's just take a quick look here. It makes sense that dh dt would not be constant throughout the whole process. Because the cone is thinner at the bottom, here the height would increase more quickly, and as you get towards the top of the cone, the height's going to increase more slowly, okay, because it takes longer to fill out that section of water. Okay, so let's input what we know. So we know dv dt is 0.9, okay, equals this big ugly thing. Well, in fact, here the 3 and the 27, I'll simplify that so there's less to put in my calculator. So pi times 1.6 squared divided by 9, and here we're given that the height is 2 meters, what we're interested in, so 2 squared, so that's 4, and dh dt is what we're looking for. Okay, so let's solve for dh dt. Okay, and let's carefully input that into our calculator. Okay, so here we've got 0.9, and we have to divide by this whole thing. Okay, so make sure you put that in brackets. So here we've got pi times 1.6 squared times our 2 squared, which is 4, okay, and divided by 9. Okay, and here we have dh dt is 0.25, and let's make sure we've got the correct units here. So here we know that the height is given in meters, so this is going to be meters, and the time unit is in minutes. Okay, so there we have it. So again, a bit of work to do on this one here, because the relationship between the two values that we're interested in contained another variable, so we had to do a substitution, and then once we had the volume in terms of height alone, we were then able to differentiate implicitly, use the chain rule, and eventually solve for the rate we were looking for. Okay, that's it for this one.